It is a physical chemistry class, and based on the focus on the interpretation and prediction of experiments, it is a very far goal that we are trying to match, at least make some steps towards this direction. And you found that homeworks, derivations, and math associated with this class is a little challenging. And there is an idea that delegating part of the functions of this class from math derivations to the computational code will speed up our learning process and achieving the goals. From now on, our main tool will be a code that solves time-dependent Schrödinger equation by evolution operator, and soon we will start projects. But let's do this session where class attendees teach each other on the principles of how this code is working. At the very final stage of presenting, there will be visitors in class, and they will ask questions primarily not about your results, but about principles, how code is working. So thank you, Ola. Thank you for joining. Dr. Han, thank you for joining. Feel free to stop and ask questions or write them later. There are eight presentations, and please try to stay within 4 minutes for each. Questions are appreciated and credited and recorded. And on Monday, please consider to turn in answers on these questions. Basically, it will be notes from what we hear on today's meeting. It is you all serve as a teachers to each other. So give details of one subject and learning on another one. So I do not doubt that you are experts in PowerPoint and Microsoft, but just in case, here are slides from first to 8, labeled by number and by name. So bring it in. Click on this little stuff. Present, and here is a microphone. Either mount or keep in hand, whatever is comfortable. Okay. So White will start with most important principles.
So covering properties of operators, the wave packet propagation, momentum, Hamiltonian, and evolution operators. So the wave packet is a type of wave function where the wave activity travels in a burst together, and it moves as like a collective group, like within its own envelope. And in the code, some of the most important properties of the wave operator is you have to determine the initial momentum and the initial position in lines 5 and 6. And the initial momentum will have a lot of impacts on any other conditions you have in the code, whether you're doing it in free space or in a box or with a wall. It's going to affect how it interacts. The momentum operator is defined as negative IH times the partial derivative of x. And in the code in line 66, you have the initial Gaussian wave packet, but that returns individual vector values. And instead, for the momentum operator, we want a matrix. And so using the definition of a derivative, we will convert the momentum, or we will make a matrix out of the momentum operator from the vector values of the wave packet. And then in line 75, you can see that the momentum operator is in a diagonal matrix. And how we convert from a vector to a matrix is we take the individual vector values of the wave function, and then we multiply a square matrix with -1 on the diagonal time, and then also 1 on the upper subdiagonal. And when you multiply those two together, you'll get the value from the position you're at subtracted by the value of the position before that. And then you continue going down for however many values you have, and then multiply times the constants negative IH and then divide by your dx. And then here's the visual representation of the matrix. So on the left side, you have the momentum matrix, or the matrix in momentum space, and then you'll get obviously values in the diagonal. And then once you convert that to position space, you'll get a visual representation like this. And in the next presentation, Joshua will cover like Fourier transforms and how you go from momentum space to position space. The Hamiltonian operator is kinetic energy plus potential energy. In line 78, you have just the kinetic energy. And in line 110, you add the potential energy to that. And then in line 59, you define what the potential energy is. And then also in line 108, right above that, that's the Fourier transform to convert the position operator to position space and take it out of momentum space. The final thing is evolution operator. So you have the past wave function times the eigen energy states to get to your future wave function. And in the code, in line 112, you have the Hamiltonian operator being multiplied times those constants to get your energy eigenvalues. And then you multiply that times your original psi function to get your future. That's it.
Okay, please join me in thanking live. Any questions to the speaker? I do have a quick one. Slide 4, please. Yes, image on the maybe next one. Image on the right.
Yep.
Do the elements of the subdiagonal elements change as you go across the matrix, or they are the same in the vicinity of main diagonal?
In the one on the right?
Yes.
They're in the vicinity of the main diagonal.
And
but
do the absolute values, do the height of the peaks change? Just as you see it?
No.
No. How, now let's go one back. So how does it relate to the matrix that you put on the left of this image? That on the diagonal and main diagonal you have the same numbers. Do you see a connection between this matrix and the right image on the next slide?
Yes.
Okay. Please join me in thanking Wyatt for answering questions.
All right, so we start out with what is commutation. So you have like A and B, and both of them represent observables. Then you have AB minus BA. And then if the result is 0, then those observables can be observed at the same time. But if not, then they can't. Okay, and then here we have the formulas for the position and momentum operators, whereas this is the wave function. And if you do take the commutation of the two operators, then you get the IH capital I, where the capital I is the unit operator, and we'll get to that later. And then using mathematical methods such as the Fourier transform, we can rewrite it as the position operator in terms of momentum. So here's the Fourier transform, and it's very important to find the position operator from momentum or vice versa. And in this case, there's two important formulas. So here's a quick conclusion for the first part. And then here we have the position operator. So it's in respect to position. As you can tell, it's a linear in 3 dimensions. So it pretty much has 3 different components. And if one component is 0, then this line would appear as a line on a plane. And then here's what I talked about before was the momentum operator. In this case, this code is using the p-op here, and this one's real, whereas this one's just for comparison with the imaginary. But then if we have, instead of using P-op, we use the PX3 and the control, that then we have this, what we've seen in the last presentation with the momentum. And as for commutation, this is what the graph looks like if you do the real, but if you try doing imaginary, then you have something that looks like this. But if we look closer in, you notice that there's like these bunch of like almost like bumpy waves there. And if we look even closer, you notice that the low points are at 0 and the high points are at 1. And what I noticed though is that the wavy fader is most likely because the Fourier transform, and the range from the 0 to 1 has something to do with the identity matrix, which is something which has to go back to the identity of the unit operator. And then here we have the example of the commutation with the S-op and PX3. And as you can tell, the PX3 is usually more accurate because like you have like this straight line at a level versus having a slope. Anyway, what we've seen in the other past slides. Here's just something that I just curious is like if I want to take like a graph and want to multiply it by a positive constant, and in this case I use in this case here you have there's the volume of between the two planes that intersect are actually increased because this one axis is increased if I multiply the graph by 300. But if I divide it by 300 of the normal one, then you notice that these values are smaller, so meaning that the volume between the two planes are smaller. So here's another conclusion, and then that should be it.
Okay, please join me in thanking the speaker.
So.
Joshua. Whew, I think I'm not too old, but the names often go so well. Okay, so any questions? I have a quick one, and I hope that right now everyone is nervous about their own talks, but when we go to the last talk, everyone will be relaxed and you'll get an avalanche of questions. PX and PX3. PX and PX3. What is their difference, and which of them gives more realistic commutation relation?
All right, I can't remember exactly the difference between PS and PS3, but I know that the PS3 ended up giving the more accurate results, even though in this case it's shown as used as imaginary.
And it looks more like identity operator.
Yep.
As you declared in your initial slides. Okay, so method based on PX3 is more reliable for everything you compute. And if method based on PX and method based on PX3 coincide, it's just a wonder. PX3 is better. More questions to Joshua? 1, 2, 3. If not, let's thank him once again.
So basically, my presentation is on modeling of quantum dynamics. So what we usually show our initial conditions, which is different depending on the person, whatever you want to do. So basically, we have a wave packet where this is the plane wave, and here is our Gaussian distribution. So basically, as I said, the P0, the P0 is our initial momentum, and X is our initial position. Basically, here I plotted our real and imaginary part of the wave function to show. And I'll focus more on talking about like the genetic methods on like following the alternative methods you get used to, like find your wavefunction. So before I talk about all three methods, I would like to stress the importance that all three methods use the evolution operator to get the wavefunction. And in order for us for the wavefunction to be used, we also need to use the Hamiltonian. And basically, method one use the momentum, the evolution operator in momentum space, whereas method 2 and 3 use it in coordinate space. So, as I said, method 1 basically use the momentum in momentum space and propagates it in momentum space, whereas in method 2, the momentum is used in coordinate space and then it's propagated in coordinate space. In method 3, the momentum is defined as the position space based on the derivative in finite differences, and is propagated in coordinate space. So basically, here's method 1. So basically, in method 1, so the momentum before was defined in coordinate space. So basically, we're trying to transform it into a matrix because MATLAB works better with matrices. So in order to do that, we use a K space, or K, basically, which K is the eigenvalue of the momentum, if I'm saying that correctly. So by using K, we basically convert our momentum operator into a matrix. And then after we have our Hamiltonian operator, which we know that is momentum squared over 2m. And yeah, basically after we type in the function, we get the method 1 basically. And then method 2 basically, as we use Fourier transform because we wanna convert our momentum back into coordinate space, and so we name it as px, and then after, which is also called as an alternative definition of momentum basically. So then after we have our Hamiltonian, which this time will be our the px squared divided by 2 plus our diagonal potential energy, and then after basically we also, using the Hamiltonian, will obtain a new evolution operator, and then after we plot our wave function. And then method 3 basically we use a Toeplitz matrix, which is basically a diagonal matrix in which all elements have the same values. So basically method 3 we convert it into a diagonal matrix, and then after we plot it, we plot that, right? Yeah.
Okay, please join me in thanking Cybele. Are we relaxed enough to start asking questions?
Yes, I have one. Is there any reason to use method 1 and 2 over method 3?
Well, I'll say that the method depends on the research. So whichever I guess method you find works along with whatever project you use, right? Okay. So whichever method works with the project, because I'm sure not all 3 methods will work with the project. So in my work with like whichever one is easier and works better for your research project. Does that answer your question?
Yep.
Okay. Excellent. So there are different definitions, and ideally they all should give the same
answer. Yeah.
But
and there may be more methods except from these 3, but this is the 3 in the code. So I don't know if there's more, but they may be. So we may decide to.
So there is a challenge how to represent derivative in finite differences. Not it's all dealing with this. More questions? So slide 7, please.
I don't know which one.
Yes, line 108. So it has symbol W
Yes.
twice.
Yes. So basically, we multiply our wave function times our momentum operator.
It's not wave function.
Sorry, the
Fourier transform.
Fourier transform by our momentum operator, and then by the conjugate of the Fourier transform.
So I'm very curious why. Just sure.
I said
if we follow Joshua and convert wave function from position to momentum, we apply Fourier transform once. And here you apply it twice. Why?
Because I'm trying to convert it back into position.
Because operator is a diagonal thing.
Yeah.
Make sense? More or less. I have more questions, but we will fail in time. So excellent talk. Thanks Cybele once again.
All right. So I'm going to be talking about numeric tricks and the normalization of discrete representations of wave functions and simulation cells that you can make with these discrete representations. So discrete wave functions in space and time, it's basically just a wave function expressed as a set of points, each having a set or discrete increment. And these correspond to position and momentum, and these are plotted against a span of time. In MATLAB, we can discretize a wave function by declaring a set number of points, NPTS, as I guess 200 in this case, to be plotted to describe this wave function. Mathematically, how we normalize a wave function, we know that our particle has to exist somewhere in space. It just doesn't disappear like that. The probability of finding the particle in all of space is 1 then for all t. Normalization will help us calculate the probability of finding the particle in an area of space at any point in time. So this is the condition of that. It just says the probability is 1 across all of space. Here's the code for psi naught, basically translated into equation form. We know we must obey that mathematical condition, so we have to include dx, which is in this case actually a discrete step size of around 0.4 in the calculation for psi naught. So if you notice, I have p sub x and then p sub or p naught there. Those I mistakenly capitalized that one over there. That one refers to initial momentum. Everyone refers to the probability. If you also know, notice I have sigma naught, and that refers to the initial width of the wave packet to be used in this calculation. This will help us build the probability distribution that defines our wave function over a period of time. So this is what that looks like in a simulation cell after it's normalized and plotted position versus time. There's another axis not shown here, but for our purposes, this is sort of the most important bit. You'll notice that the range of possible positions kind of widens in time. That's kind of what we expect from, I guess, any sort of wave function. What should also be noted as the initial momentum in this, I set it to 2.25, and that's high enough to where this actually makes the function kind of extend. It looks like off screen. It looks like it bounces back. That isn't some strange motion of the particle. That's just because the bounds of the simulation cell are not big enough, and after it reaches the wall, we're still measuring it over the remainder of the course of time, so it has to rebound to 0. The position of the particle did not. It kind of exceeded the maximum boundary position in this case. This is a better way to visualize it. Essentially, you can just see it extending past this simulation cell. All right, questions?
Okay, please join me. Thank you, Adam. Any questions? I have two combined into one. Are there problems where this passing of wave packet through boundaries is okay and doesn't undermine our results? First part of the question. And second, if it is a bad effect, what can we do against it if we still need to have job done and we want to avoid it? Like, which practical steps can we do to avoid passing of the wave packets through the walls?
We could just increase the boundary space. No, I guess the size of the cell.
Yes, and
the or we can set the initial momentum lower.
Perfect.
Okay.
Yep.
Your first question was, can you repeat it?
Other classes of problems where passing of the wave packet through boundaries is absolutely okay and doesn't create any problems.
Yeah, you measured or you mentioned something yesterday about, or not yesterday, a couple of days ago in lab about when calculating, or when using calculations to describe like cells, unit cells of polymers that are semiconductive.
Yeah. Okay. More questions? If not, let's say I don't know.
Yeah. So my presentation is all about observables and applying them to formulas for later analysis, I suppose. So calculating the expectation value of any observable, you can normally follow this equation. You plug in the operator into this integral of the wave function over space. So in the code, there were 3 examples of this: momentum, position, and energy. And you can see for momentum, we plug in the momentum operator, position, the position operator, energy, the energy operator. And over here is the examples in all the codes. So method 1, 2, 3. But you can see it's just the wave. It's just plugging in that operator into the wave function equation, and it's also normalized. Here is a plot of those expectation values for position and for momentum. P now was set to 0.75, so you can see when it's crossed over the boundaries of the cell for position right there. And momentum there's slight errors, but it's close to 0.75, and it's just going to stay constant the whole time. The uncertainty of position and momentum. We learned in class that as time increases, the uncertainty of position is going to follow a quadratic graph, and as you can see when you plot this this standard deviation of the position, which is calculated by variances, and it's put into an array as the code goes forwards and through the loop. And for momentum, we learned that it is held constant. So these are really small values, so it's essentially staying at 0 the whole time. And it's similar, just standard deviation, it's accumulated into an array. And this is just a plot of that array. And maybe I should have talked about this earlier, but accumulating the expectation values into an array, as it's going through this loop, it calculates an expectation value at that specific time, and it puts it into an array at each increment. And as it loops, it does this for every expectation value, whatever you set it to. I think it was 200. And at the end, you can use that array you can analyze it. Saving numerical data into files, just kind of an extra thing that I had to talk about. You just type this, you type the variable you want saved. Right? No, you this is the name of the file, and then the variable that you'd like to save for the array.
Okay. Please join me in thanking Nate. Any questions you wanted to ask about programming this expectation value convolutions? Which observables do you like it most?
Momentum's really easy, I feel like. I couldn't find in the program like an accumulation of the energy expectation. Yeah.
So you would like to add it?
Yeah.
As a little programming exercise.
That could be something. Yeah, I don't think it'd be that hard even.
Okay, yeah. But it would be valuable. Yeah.
Yes.
Thank you. More questions? If no, let's thank Nate once again.
Okay. This is about visualization, and so we'll be visualizing real and imaginary parts of a wave packet as shown here. This is the real part. As you can see, the all of the parts of the curve are above the zero, and then this other side is the imaginary side, which is kind of oscillating between the negative and the positive side. Visualizing potential and probability distribution of a wave packet. So these two curves are showing the probability density of a Gaussian wave packet. It starts at 0. With increasing time, the packet moves to the right and broadens. So the first part where you have 20, and then this other side, it kind of shifts to the next one. Okay. And this is these show the expected position and the uncertainty. So the dark dotted lines being the original wave function, and then the blue lines, the potential, and the red lines being the probability distribution. To visualize any observable on MATLAB, you just type in plot x, comma v, where v is the independent variable and then x is the dependent variable. You can modify this code depending on what exactly you want to achieve or how complex you want to make things. You can group data on MATLAB using the G function, and when they are grouped, you can also have them all plotted on the same panel to prevent having several like different panels popping up at the same time. So you use this code figure to generate to do that. You use figure and then subplot. Have all of these codes as shown here, and then you have panel 2, the ones for that, as well as panel 3, and then you can have all of these in one panel, all of the figures.
Okay, please join me in thanking Mike. So you hear applaud in the class. And what are other questions? I have a quick one, and anyone is welcome to raise hand and ask. Would you please go to slide number 5? Yes. So no, one forward. Forward.
Forward. Okay.
Stop here. So in the central panel, the thick red line shows oscillations, and in all previous speakers were showing that position changes linearly. So likely this code was you executed it for different potential, not for the free space, but for some specific potential. And everyone is in class is welcome to help guessing. So what was the potential? Go back to this oscillating backwards.
Okay.
Yes. So which version of the code was executed, or how did you modify the potential to get this oscillations of position? Anyone who knows the answer can give a little hint, raise hand.
Probably in a box.
Huh? So one version is
In the box.
okay. Nate, same. Any other opinions? And you are main author. So what was the? Please answer why these oscillations are coming. What was the potential? Any other opinions? Because my opinion is different from your box. And just project back on what we studied before in class before diving into this activity.
Oh, I don't know.
Come on, do not surprise me. So why position is oscillating? What would be the potential?
I'm thinking, just like in the box. Like,
A box. Well, there are some whiskers on the side, something returning feedback, but are they straight lines going up or something different? When center of the wave packet oscillates?
When does the center of the wave packet?
Yes. For which potential? For which system? Let's keep thinking, and you can shoot from the place.
It would be a negative.
Well, potential goes up and it returns. It may exert force on the particle.
So it'd be a harmonic oscillator.
Yes. So Joe is our champion. Thank you. So I pass your thanks to Joe because he answered your question. Do you agree?
Yes.
Okay, very good. Any more questions to Mai? 1, 2, 3. If no, let's thank her once again.
Yep. All right. So basically, everyone else did the work for me. I get to piggyback and show you a fun movie. So what we're looking at here is the wave packet and how the concept of waves. And we want to look at two different waves and how they interact side by side. And MATLAB gives us the ability to show these through code and to run it. So from the basics, we see showing there is an equation, and we can also see the waves are superimposed, which are at different frequencies, which is why we see the difference in them. So basically, we're going to run the code, that long code that we were given. So we can insert the code into MATLAB and run it, and we can see the position of these. We're going to start with the real, as was said before. We can start with the real image, and basically what's going to happen is that we can see that once we press the space bar, we are going to see the momentum operator function. And so we can see different variations of these waves dependent on their momentum, and we can change those momentum. So we can see at our momentum on the top at 0.25, and we can see how those waves are kind of coming closer together. As where you put the momentum as 0, they're going to go like they're not coming as close together, but they're going to be farther off in the distance of that momentum. Again, I'm no genius at MATLAB, but looking at these loops, we can see how we can continue the video and show that the momentum is increasing. And these loops look something like this. Both these are examples of what we are using in our codes. So to view the movie, we're again pressing the space bar, and the momentum is going to continue, as we all know, the long momentum. And then at the end, we are given these values of these observatives that are the position and what we can expect to see from the momentum. And then we get to upload to YouTube so everyone can see what we're doing. So basically, you're going to open the YouTube up online. You're just going to hit create. You can upload your file as an MP4. And once you do that, you can make a title, make sure it's not for kids. I don't know why, but they can't see MATLAB yet. So we're gonna press that, no kids, and then you put a title, obviously by the best professor ever sent us the code, and then we are going to upload it to YouTube, and it's gonna look something like this. Well, do you want me to go out and click on the video?
If you navigate to the bottom of your try to from the bottom of this white panel, white panel with image.
This one? Oh.
Just put in this.
Oh, there we go. And we're slowly watching the momentum increase. So very intriguing, slowly going. All right, so we can see that and we can observe what is actually going on here. Let's see. And once again, it is important to showcase what we're doing so everyone can see it. Our quantum idea can observe the wave packets and gain knowledge from what these waves are producing. Yep.
Okay, please join me. Thank you, Allison. Questions to her. I know we are almost out of time, but I have two questions.
Okay.
So, can you scroll to slide number 5? And the question is to everyone. 5 backwards. Yeah, stop here.
Okay.
So, what if anyone has answer, please raise hand or just shout from the place. What is on the y-axis? It shows probability, but probability of what? And it is kind of advanced question because we didn't cover it in the labs. So what are you showing for momentum of 0.25 and momentum 0? What are these lines that start at 0 and 1 and then intersect?
Is that the frequency?
No.
No.
So if anyone has even a rough idea, please do not hesitate. Wait.
Probability of density.
Repeat.
The probability density.
Probability density. Well, maybe just probability, but probability of what? Any ideas? I will give the key in a minute, but please focus on it. We will need it for projects. So something that happens more vividly if we increase the temperature, the momentum. How do you connect it to the chemical reactions? Like if you, yes, so it's probability to form a product of reaction. As reaction goes by, probability to find a product grows from 0 to like 20% or 50% or goes completely. Make sense? Okay, and question number 2, go forward, couple of slides. Stop. So it's a very tricky question. If you do not answer, I'm completely do not mind. So let's look on the lower right. You see the panel is labeled as sigma sub x, and it shows dramatic peaks that appear again and again. So anyone can interpret what are those peaks. Like the width of the wave packet should grow quadratically, and here it grows and then drops. The best person to ask to answer it based on today's presentation is Adam. But question is, do you, Allison, if you have any ideas, please try and help is appreciated, especially from Adam.
Thinking. We got any ideas?
So what did Adam taught us?
Thinking.
What was with
the tricks?
Tricks, and the second part.
The second part.
Passing through the boundary conditions. So what happens if the first half of the wave packet passes through the border and second did not? It looks like it is extended over the size of the box, and it is an artifact of the method. The width of the wave packet for the very short time looks like huge, like 100 or size of the box, and then when it completely passes through, it becomes small again. Make sense?
Yeah.
I was fearing this question for many years. Okay, more questions to Allison? If not, let's thank her once again.
Okay, so I'm going over applications of our wave packet code. So one application for the infinite or finite box, as the wave packet travels along the horizontal axis, it'll start to bounce between, it'll start to kind of like bounce in between the boundaries of the box or the dimensions of it, which is, you can kind of see here as it's kind of contained within the dimensions of the box. But still, there's a little bit of potential energy that's able to escape these boundaries because the higher the momentum is, the more energy that you'll have to overcome these boundaries. And this kind of applies to both the box and the barrier as well. As far as like how this is useful for like chemistry, it's really more to help model complex physical systems, such as like movement of electrons or energy of electrons through complex like polymers and other things like that. For the barrier, as the wave packet will travel along the axis, it will stop at that barrier part right there, and kind of reflect backwards in the opposite direction, as you can kind of see here in the density graph, where it around here is where it kind of just reflects in the opposite direction. And again, as you can see, a little bit was able to make it through past the barrier because it had a high enough energy level. And then this is useful in chemistry, as I think we've mentioned previously, for activation energy. It can help us figure out what we need to overcome that energy barrier to get a reaction going. The harmonic oscillator, it moves a bit differently because as it moves along the horizontal axis, the center of the wave packet travels in the shape of this parabola highlighted in green, and that can kind of be seen in this graph here as it kind of moves back and forth. And this kind of applies to chemistry for molecular vibration in diatomic molecules.
Okay, yeah, let's thank Joe for convening a lot of different information in a short time. Anyone wants to please him with a question? Or it was so crystal clear that the only way we can do is to applaud him once again. Okay, let's do it. Thank you. So many thanks to everyone for making this outstanding presentations. So they are credited as a successful midterm, and from now on we will primarily focus on the research project. So I apologize for giving you homework after your well-deserved relaxation, but we need to just finish in time the semester activity. So wishing you to have a nice, as much as possible, nice weekend, and looking forward to see you on Monday. So meeting is done. Many thanks for presenters and for attendees for joining us, and see you again.